Chapter 20, Heat and First Law of Thermodynamics. In this chapter, we're going to learn something about thermal energy, that is heat. Well, there's a couple of terms that we're going to clarify first. The first one is called internal energy. And internal energy actually is the internal energy of a system. For example, if we have a container which contains gas. The gas has internal energy even though this container sits on a table. From a microscopic view, the container physically doesn't move with respect to the table. Therefore, if we use the table as reference, there's no kinetic energy as the container itself. However, because the gas molecules or atoms are constantly moving inside, so there is so-called thermal energy. Thermal energy is due to the molecular level of kinetic motion that is defined as thermal energy. There's something else called bond energy. So the bond energy actually is intermolecular potential energy that is between the molecules. Actually, between the molecules, there's kind of potential energy, and also with intermolecule, which is within the molecule. For example, O2, if you want to break the two oxygen atoms, that you have to break the bond. That is the so-called bonding energy. So the bonding energy basically is between atoms. That's called intermolecular. So that is a oxygen atom. That's another one. For example, you have a H of H2O. That is the bonding. That's the bond. Here is the bond. So the bond energy refers to the intermolecular, and the thermal energy in our case, it is pretty much refers to that the kinetic energy of atoms or molecules. Therefore, we do not consider the potential energy between the molecules. That potential energy could be gravitational potential or electric potential. Okay, so the thermal energy is a kind of random motion of molecules. That is something to do with, we say it's proportional to the temperature of the system. The next one is about heat. Heat is pretty much the definition of thermal energy. Heat can be only measured when the thermal energy has been transferred across the boundary of a system due to a temperature difference between the system and its surrounding. For example, we cannot ask how much heat does a system possess. We can only measure how much heat has been transferred between the system to another system, or say between the system to its surrounding environment. So heat can be only measured when the thermal energy has been transferred from the system to the surrounding, or from system to another system. Since heat is kind of thermal energy, well, in the mechanics, we use Joule as the unit. So we have the freedom of using Joule again, but traditionally we have another unit which is calorie. Calorie is a traditional unit for heat. Another one is also pretty popular, is called British thermal units. That is also traditionally used to describe heat. That's the unit for energy, thermal energy. So the conversion between calorie and British thermal units is 1 BTU equals 252 of calorie. So that is between BTU and a calorie. However, if we want to know First of all, what is the definition for calorie? Second, what is the connection between calorie and joule, and where did we get this conversion of 1 calorie equal to 4.186 joule? Then we have to talk about an experiment called the mechanical equivalent of heat. So let me first introduce the definition of a calorie. Well, 1 calorie is the amount of energy, or thermal energy, transferred necessary to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. It's pretty strict. So it is from 14.5 degrees Celsius goes to 15.5 degrees Celsius for 1 gram of water to increase this amount of temperature. The energy, the thermal energy in need is defined as 1 calorie. And between the calorie and the mechanical energy unit joule, there is an experiment. Let's look at this device. This is a device that the conversion between calorie and joule was conducted. That James Prescott Joule was a British physicist, and he conducted this experiment to get the relationship between the thermal units of calorie and the mechanical units of energy of joule. The idea is this is a chamber filled with water, and this is the rope, pulley, and the mass. Imagine that if we let the block, both block drops, and there is a decrease of its potential energy, gravitational potential delta U equals to mg of delta H. So if the height of the block is lowered and then its potential energy drops, the potential energy actually goes to, what happened is, from energy point of view, this system potential energy drops, and a part of energy will go to, because of friction between the rope and pulley, part of the energy will goes into this system. Why is that? Because when the block drops, the tension on the rope will create the torque. It will make this axle rotate, as this showed as omega. So when the axis rotates, the pedal inside will stir the water. So the pedal does work to the water, and water gets warmer. This is a science thermometer. It can measure the change of temperature. The other one, actually, when the other one drops, it creates a same direction torque, because this rope is behind this axle. So it's going to create torque of counterclockwise, and this one, the rope is in front, so it also will create a counterclockwise torque. So both drops will create a counterclockwise torque and make the axle rotate, and the pedal spins and stir the water, and the temperature water rise. So as we know that when temperature of the water rise, which means it absorbs energy, well, the energy actually comes from the potential energy of these two blocks. So we can calculate how much potential energy is lost. Well, obviously in this case, if both drop the same height, and we just need to double this m because of the same mass of block, and then we can calculate what's delta U, and then by measuring the change of temperature, we'll be able to figure out how many calories heat is absorbed by the water. So we have a conversion between, because delta U is in joule, and the heat absorbed by the water is in calorie. So if we make them equal, and we will be able to find a ratio. That is the so-called mechanical equivalent of heat. Okay, let's come back to where we start. A system which has internal energy, which is the summation of thermal energy and bond energy. Most of the time we do not consider bond energy, we consider thermal energy. And when thermal energy has been transferred between the system and environment, we say heat has been transferred. when we measure heat, we can either use calorie or BTU or Joule, because all three are units for energy. Now the ratio between calorie and Joule comes from the experiment called the mechanical equivalent heat, which was conducted by James Prescott Joule more than 100 years ago. Now, we mentioned that experiment by saying that if we know the change of temperature of the water in the container, we can calculate how many calories heat has been absorbed. Exactly how do we do that calculation? In order to do that, we must introduce a concept called specific heat. Well, obviously that water absorbs heat and a temperature raise. So we say the amount of heat, that's energy absorbed by the substance, divided by the amount of mass. The mass doesn't matter, because if you have more water, you deliver the same amount of heat, change of temperature will be smaller, right? So we just say for a particular amount of mass, change delta T a particular amount, and if we know how much energy is being absorbed, the ratio defined as specific heat. So once we know the specific heat of every substance, then it is pretty easy to find, if we know the mass, if we know the temperature, if we know the mass, if we know the temperature change, if we know the specific heat, then we can calculate how much heat has been absorbed by this material. So specific heat and calorimetry, as a matter of fact, is based on this concept. On your textbooks at page 600A, we have a table 20.1. Table 20.1 listed the specific heat of solids and liquids and gases. So there's a couple of pretty useful ones. For example, if we look at a table 20.1, the specific heat for solid, say for example C for aluminum is 0.22 of calorie per gram per degree Celsius. That is one column. That is based on calorie per gram per degree Celsius. That means 1 gram of aluminum, increased temperature by 1 degree Celsius, it absorbs 0.22 calories of heat. On the other hand, that if we use SI unit, that gives us 900 of Joule per kilogram per degree Celsius, which means 1 kilogram of aluminum, increased temperature by 1 degree Celsius, it needs 900 joules of energy. So we can either use this unit or the other one. Now, there's a bunch of specific heat value for other solids, for example, copper, gold, iron, lead. And the other useful one is look at the liquids. Specific heat for liquid H2O is very large, 1.0 calorie per gram per degree Celsius. As a matter of fact, if you look at it, this is the largest specific heat listed by table 20.1, which means 1 gram of water, increased temperature by 1 degree Celsius, it absorbs 1.0 of calorie. So which means water will be able to absorb a lot of heat without raising temperature too much. This is why that near the beach, the air temperature is relatively lower, because the ocean will be able to absorb the heat from the air, will absorb most of it from the air, but without raising its own temperature too much. So this is because the property specific heat of water, and that's why we use water as the main liquid for coolant, let it to cool down our system, especially let's say car engine or other hot